So what if AI didn't just learn from data, but actually understood the laws of physics? Today, we're going to dive into a pretty new frontier of artificial intelligence. We're going to explore how teaching AI the fundamental rules of our world can lead to smarter and way safer machines.
But let's kick things off with a really important question. We're putting AI in charge of everything, from our cars to critical infrastructure. But what happens when that AI runs into something it's never, ever seen before? Can you really trust it with your life if it's basically just guessing based on past events?
And look, this isn't some far-off theoretical problem. It points to a really dangerous blind spot in how we usually build AI systems today. Let's actually look at a real-world case where this exact issue popped up.
Okay, so check this out. An AI was trained to predict the physical strain on an aircraft's wing. And as you can see on the left, for normal flights, the stuff it was trained on, it was incredible. Super accurate, with an error of less than 1/3%. But look to the right. When that same plane hit unusual conditions, like low altitude and some heavy turbulence, that error just skyrocketed to over 4%. The AI failed, plain and simple, because it had no clue what to do in a situation it hadn't seen before.
And that right there is the heart of the problem. Your standard data-driven AI is kind of like a student who's only memorized the answers to old tests. It's never actually learned the subject. So when you give it a new problem, it just breaks. It can't solve it because it doesn't understand the underlying principles, the actual physics of how things work.
So, to really wrap our heads around the solution, we first need to understand the different kinds of models out there. And it really helps to think of them on a spectrum, from what we call a white box model all the way to a black box model.
On one end of the spectrum, you've got the white box. This is pure physics. Think of those really complex differential equations you might have seen in a textbook, the ones that describe exactly how a system is supposed to behave. These models are awesome because they're totally transparent. You know exactly why they make a certain prediction. The only problem? The real world is, well, it's messy. And these models can be way too rigid to capture all the chaotic variables.
Then, on the complete opposite end, you have the black box. And this is our aircraft wing AI from before. It uses things like neural networks to learn directly from just tons and tons of data. It's super powerful, it's flexible, but its decision-making process is a total mystery. We can't see inside. And as we already saw, it's incredibly brittle when it faces something new.
So there you have it, the two extremes. On one side, the white box of pure, clean physics. On the other, the black box of pure, messy data. But the real magic, the solution to our problem, lies right there in the middle, what we call the gray box, or hybrid model.
And this gray box approach, this is where things get really cool. It's all about teaching the AI the actual rules of the game. It's about combining the absolute best of both worlds to create something that's way more robust and, frankly, trustworthy. Let's see how it works.
Now, this approach actually has a name. It's called physics-informed machine learning, or PIM for short. It's basically a method that takes a flexible, data-driven AI and gives it a foundation of fundamental physical laws. So it doesn't just learn from what it sees in the data, it's also guided by what it knows has to be true about the physical world.
The researchers who developed this put it perfectly. The goal is to merge the raw power and flexibility of machine learning with the deep, structured insights you get from physics. The data-driven part handles all the complexity and the messiness, while the physics part provides this solid foundation, almost like a safety net.
All right, so all of that theory sounds great, right? But the real question is, does this stuff actually work out in the wild? Well, let's look at two really fascinating case studies where this smarter, physics-informed AI was put to the test in some pretty critical situations.
First up, the Tamar Bridge over in the UK. So here was the challenge. Predict how the bridge deck would move and bend during the cold winter months. But the AI model could only be trained on data they collected during the much warmer autumn. That is a classic and really hard prediction problem. And the results, they're just stunning. The standard black box AI, the one that only used data, was completely lost. It had a massive error score of almost 69%. But then look at the gray box AI. By giving it just one simple physics rule about how materials expand and contract with temperature, its error plummeted to just over 7. That's nearly a 10-fold improvement in accuracy, a total game changer.
Okay, for our second case, we're trying to find a hidden crack in a metal plate using acoustic sensors. Sounds straightforward enough, but here's the catch. The engineers could only put sensors right in the middle of the plate. This left the AI totally blind to what was happening near the edges.
So how in the world did the gray box AI figure this out? Well, it was actually pretty elegant. First, it was given a map of the plate's physical shape. Then it was told a simple rule. Whatever you predict, it cannot go outside this map.
So even though it only had data from the center, these physical constraints acted like guardrails. They helped it make much more intelligent guesses about where the crack could be, especially at those edges it couldn't even see.
So you can see, these examples aren't just neat academic exercises. They point toward a future where we can build AI systems that we can genuinely, truly trust with our safety.
So what's the big takeaway from all this? Well, by embedding real-world physics, we get AI that is just safer and more reliable. It can get incredible results with less data because it isn't starting from a blank slate. Its decisions become more understandable to us humans. And maybe most importantly, it gets much better at generalizing, at handling the unexpected by falling back on the fundamental laws of the universe.
And this kind of brings us to a final thought I want to leave you with. There's no doubt we are building a smarter world, one that's powered by artificial intelligence. But I think the real challenge, the real question, is how do we make sure that this intelligence is also paired with wisdom, a deep, foundational understanding of the world it operates in? Physics-informed AI, well, it might just be the key to doing exactly that.